Steve.
Okay, well, thanks. I'm glad I'm having a chance to be here. This is going to be more in the nature of a seminar rather than a pedagogical lecture, although I will try to go slow, and I'm happy to be interrupted whenever. If I don't get through everything, that's fine. You can ask Douglas about it tomorrow. This is directly builds on what Phil Saad has been telling you about, I think, earlier this week. I don't have a thorough understanding of what he talked about. I just quickly looked at his slides a few minutes ago. So I may repeat some things he said. Hopefully that will not be completely useless. So the subject we're going to talk about is a subject that's been a lot of recent interest, the subject of wormholes and what their role is in these modern issues involving black holes and information loss, and the way that the boundary theory in ADS-CFT fits together with properties of the bulk. So let me just give a brief introduction, and I know Phil talked about this before. I guess because this is a school, I'm old, as Tom DeGrand just reminded me, I should try to give my current jaundiced view of where we are. Our best understanding to date is these wonderful ideas of gauge gravity duality, but these came on the scene maybe a quarter century ago. And I think the current status is, at least in many circumstances, we understand the boundary. We more or less understand what super Yang-Mills theory is, to the point where we could probably set up computer calculations of it if we allow ourselves some fine tuning. But we still don't know all the rules of the bulk, the thing it's supposed to be dual to, gravity. We know many things about it, but we don't know, to use a phrase, what is the gravitational plus strings, brains, and stuff path integral? We don't have a complete formulation. Maybe to be more poetic, we don't know what quantum gravity is. Well, there are puzzles that illustrate this sharply. One of them that we'll focus on here is the factorization puzzle. And in this context, it was introduced by Maldacena and Maoz. There's a paper of Witten and Yao's that discusses closely related things around the same time. So in the ADS-CFT context, consider two decoupled systems, L and R, like two copies of super Yang-Mills theory. And compute the partition function of the combined L plus R system. Well, when you take stat-mech, you combine two quantum systems, you take the tensor product of the Hilbert spaces, and compute the partition function, let's say the thermal partition function of the combined system. Well, it obviously, because of the properties of tensor products, factorizes. And I can draw a picture of that. There's a left thermal time circle and a right thermal time circle. And the combined system is just this. It's trivially the same as this times this. But now you might try to compute this gravitational. Now, one popular set of rules to how to do the gravitational path integral, and it's just popular, it's not proven, and it works in many interesting contexts, is to take the boundaries and fill them in with whatever bulk geometries fit in. Usually you look for solutions. Well, if you have these Euclidean boundaries, you can put things that are topologically a disk on each boundary. These would be like Euclidean cigars, Euclidean black hole geometries. Well, there's another geometry that you can naturally draw, which is a wormhole, a configuration that connects two sides. This is like Euclidean time, so this is a space-time wormhole. Okay, it's distinguished from, let's say, an Einstein-Rosen bridge, which I'll call these spatial wormholes that we also talk about. Well, in simple models of the kind Phil has been talking, like JT gravity, surfaces are weighted by e to the Euler character times something called the ground state entropy. The disk has Euler character 1, it's weight e to the s. This has e to the s, this is weight e to the 2s, and this is weight 1. Well, a crucial thing about this picture is that it doesn't seem to factorize. I was about ready to try to cover up my screen, but I realize I can't. If you try to compute z left times z right, you just get this part of the picture. The combined system, you have this part as well. The wormhole is an obstacle to this factorization condition. Okay. Now it's order 1 compared to e to the 2s. It's a small violation of factorization, but in certain circumstances, it will be leading. And in any event, this is supposed to be a precise equality. Small deviations mean we don't understand something. Well, I think in earlier times, maybe 10 or 15 years ago, people, probably including me, would have said, perhaps you just shouldn't include wormholes in the gravitational path interval. Oh, they're unstable, they don't lie on the correct integration contour, something like that. But what's changed recently is that these configurations are turning out to be useful. There's this thing called the eternal traversable wormhole. There's something we'll focus on, the long-time behavior of the spectral form factor and correlation functions. We'll focus on this. I think Phil has talked about this. Then there's this page curve and squared matrix elements in the replica wormhole story of evaporating black holes. And then there are extensions to this with higher dimensional situations and plausible candidates to find there. But some of these examples, like the spectral form factor, involve decoupled boundary systems, the kind we talked about just now. And so the wormhole explanation, which seems to work, at least in some respects, raises a factorization puzzle. So if you want the good stuff, you have to accept the bad stuff. And so we're going to have to confront the bad stuff. Well, the control calculations for wormholes in these factorizing quantities, like the spectral form factor, are done in simple models described by ensembles of boundary systems, as Phil has told you. Two of the main ones are this famous SYK model, which we'll say more about later, and JT gravity. This is dual, as Phil has taught you, to an ensemble of random matrices. If I denote ensemble averaging, that means a probability distribution of quantum mechanical systems by these angle brackets, then the ensemble average of the combined system is not equal to the product of the ensemble average. Well, anytime you have averaging of something that has some non-zero dispersion, it'll obey something like this. And so there's no factorization puzzle. Now, in fact, this link between ensembles and wormholes has a long history. It goes back to the work of the 80s of Coleman and Giddings and Strominger. Work that's been recast recently by Marolf Maxfield in the ADS CFT context. And this is a really interesting paper for those of you that haven't looked at it. Well, what you get is some kind of what's called a third quantized universe field theory description with multiple copies of circular JT baby universes. We won't talk a lot about this, but you should just be alert that there's a dramatic proliferation of things that happens here. Well, in these ensembles, you don't have a factorization problem, but you can ask a version of the factorization puzzle in a place where we have some control. You can say, what happens for one element of the ensemble? SYK is a system of fermions coupled together with kind of random couplings. What happens if you take one draw from those distributions? You have one fermion Hamiltonian. Now, it's a basic result that if you're in a situation where wormholes dominate, then the variance of the combined system, which is the average of the square minus the square of the average, is of order the signal squared. That means there's lots of fluctuations, okay? If the standard deviation is of order of the signal, that's a lot of fluctuations. Well, how do you calculate this? In the bulk, it's easy to see. You compute the square of this combined system by doubling. Here's the LR boundaries, and you have a doubled auxiliary set, L prime and R prime. And then you draw the geometries that link them together. Well, there is the original signal, LR. There's the same thing. So this is the signal squared. But then there are other ways to connect these boundaries. You can connect L to L prime and R to R prime, or this cross diagram. These look a lot like Wick contractions. And in fact, there's a close parallel. Well, so then to compute the variance, you subtract off the signal squared, and you see here that the variance is twice the signal squared. All right, so the answer depends sensitively on the element of the ensemble. It's noisy. choose one set of couplings, you get one answer, you choose another set of couplings, and you get an answer that's a factor of 2 different. Well, take this SYK ensemble and compute the spectral form factor that Phil gave you the formula for, basically this Fourier transform of the energy level spacings. And you have one set of these fermion couplings that we'll call J. And here's the picture. This early part, which we call the slope, is the thing that's described by, it's a 2-boundary quantity, the spectral form factor. It's like Z left, Z right. This is the 2-disk contribution. It decays, that's an analog of quasi-normal mode behavior. And then there's this ramp and plateau that, as Phil has taught you, is a signature of random matrix statistics. The blue line is the ensemble average. It's about 1,000 hours of computer time. And you have 90 samples averaged together. And the red is if you take one sample. Now this is a log-log scale. So this is exponentially smaller than this. That's consistent with that topological pattern. And these are exponentially long times because the level spacing in the spectrum is exponentially small compared to its width. So long times is when you start seeing level spacing sensitivity. Now you can argue, for instance, from JT gravity or from, as we'll talk about, random matrix universality, that the autocorrelation time of this noise is short. Basically corresponds to the energy window you're looking at. And so you can think of different times as different elements of an ensemble. And so this noise as a function of time is like the ensemble noise. This is about random matrix statistics. This ramp and plateau are signatures of random matrix statistics. And a very important point that helps guide us is random matrix statistics are supposed to be universal in quantum chaotic systems. Things like super Yang-Mills are supposed to be quantum chaotic at high energies. Okay, we can calculate things like Lyapunov exponents. Any gauge gravity dual system we think is highly chaotic. And so those systems should obey random matrix universality, which means they'll have curves like this. In particular, super Yang-Mills should have a curve like this red curve. Okay. So looking for this is not just a fool's errand. It's not some toy fermion system. This is something that it should occur in all the gauge gravity dual pairs that we know about. And so we're forced to ask this question: what accounts for the noise in the bulk description? Because it's sort of the same size as this wormhole contribution, it turns out it's going to play a role in restoring factorization. So understanding the noise and understanding factorization are 2 parts of the same question.
May I ask a question?
Yes, please.
Thank you. You mentioned that we expect this behavior from a gravity theory as long as it basically have a gauge dual.
Yes.
Is this true in any dimension, any kind of theory, or is it particularly focused on SYK, this discussion?
No, it's we believe it should be true for any kind of quantum mechanical system. They could be ordinary quantum mechanics, could be quantum field theory in 1 space dimension, 2 space dimensions. Could be, some cutoff quantum field theory in 7 dimensions. The crucial thing is it's chaotic. Like, for instance, free field theories, where the number of quanta in every mode is conserved under time evolution, would not display this. But chaos is a generic phenomenon. And so as you know, we can compute certain aspects of chaos using the bulk gravity. So there's very strong evidence that the ones that have nice Einstein-type black holes in their bulk will be chaotic. Proving that implies these random matrix statistics is a big open problem. But it is enormous, it's kind of got the same status of saying, oh, thermal systems equilibrate. It's this enormously widely held belief buttressed by lots of examples and approximate calculation. Is that enough of an answer?
Yes.
Okay. Thank you.
I also have a question.
Please.
So you're saying that, like, for example, like black holes, you should model those as these chaotic systems. But what about like something like pure ADS?
That would be, yeah. So when you have a Hamiltonian, chaos is a distinctive characteristic of high energy states. So you have to look at states with energies large enough that you basically have thermal behavior. So that's energies above the black hole threshold. So in super Yang Mills with n colors, that would be energies of order n squared. Vacuum ADS is kind of at the very low bottom of the spectrum. You know, you have vacuum ADS plus 1 graviton, vacuum ADS plus 2 graviton. There are big gaps there. Those are low entropy situations. You need lots of entropy before you can start talking about chaos.
Okay, thank you.
Okay, yeah. Other questions? I'm happy to answer questions. It's probably more valuable, and you can look at the slides later. Okay. Okay, well, so we talked about this spectral form factor. I don't even know if I defined it. It's this quantity. It's this product of two partition functions. Why didn't I should have defined it. I guess I was assuming Phil had defined it. Of Z left continued to complex time times Z right continued to complex time. But there's an even simpler diagnostic, which is just, let me get this mouse out of here, which is just one partition function as a function of real time. Instead of e to the minus beta times the energies, it's e to the minus beta plus IT times the energies. So it oscillates as a function of time. The behavior of this thing is, well, it rapidly goes down to 0. This thing is basically the square of that in this region. But then after a certain time, that when this ramp starts, you find that the thing oscillates around 0. Its average is 0. But for a given draw off the ensemble, it just has this random noise. And the variance of this noise increases like t. So the square of this, that gives this linear ramp. So the square of this for one draw of the ensemble produces a noisy ramp. It factorizes. This is just the, well, a modulus squared of this. It's just a number squared. And it contains, as Phil had told you, this ramp is a signature of a wormhole. It contains the wormhole signal. And for instance, after you time average to get rid of the noise. So there seems to be something like a wormhole signal in a single sample from the ensemble. And again, this noise and the factorization puzzle are part of the same question. So how can we attack it? Well, we can look for the bulk description corresponding to one element of an ensemble. There's a model that Maroff and Maxfield introduced you can study. These things are called alpha eigenstates in that setup. Looked at how factorization works there. In JT gravity, you can imagine not taking an ensemble of random matrices. You can imagine taking one random matrix with fixed eigenvalues. This is what this group calls eigenbrains. It's an interesting paper also. Well, what I want to talk today is about another system, this SYK model, which I'll talk about more concretely, with a single fixed choice of the couplings between fermions. And it will have some interesting features. Well, I guess I haven't written down the model. I don't know. Did Phil write down the Hamiltonian for SYK? I can't. All right. So you imagine you have a Hamiltonian that's, let's say, sum over A, B, C, D equals 1 to n. Psi A, let me do it the other way. J, A, B, C, D, psi A, psi B, psi C, psi D. And I'll put little hats on these to remind you that these are quantum mechanical fermion operators. And J, A, B, C, D is a way that 4 fermions are coupled at a time. You have n total fermions. And it's a random variable. It's a Gaussian random variable. You pick the variance to be, so you have a nice large n limit. And that's the Hamiltonian. So we're imagining just picking a fixed set of these. Now, usually what you do is you compute various quantities in this Hamiltonian, like partition functions, averaging over the ensemble. That's what gives you power. And the usual way you do that is you compute in terms of collective fields. In condensed matter physics, they're called Hubbard-Stratanovich fields. In high energy physics, you sometimes call them auxiliary fields. And here's an example. We're going to want a field for, let's say, the left-hand system that's this composite of fermions. And we say we reproduce this composite of fermions, we rewrite it as a bilocal in time bosonic variable. And we'll constrain this to be an equation. And then we'll look for saddle points in this field at large n. And the connection to the bulk is that at low energies, the SYK model at low temperatures in the thermal state, the rule for finding saddles here is remarkable. You go to, this is a one-dimensional quantum system, just as a function of time. Its bulk dual is 1 + 1 dimensional, one space, one time. The low energy bulk dual is this two-dimensional theory called JT gravity that Phil has explained to you. And the rule is you find some kind of geometry in JT gravity, it'd be good if it's a saddle point. Compute a correlator between two bulk fermion fields that live on the boundary. And that correlator is the value of this saddle point. So this variable codes geometry in terms of correlation. Okay, instead of studying metrics, you study correlations on the geometry. And so this is going to provide an example of a bulk theory, a proxy for a bulk theory. This is kind of going to be a proxy for bulk variables. I guess I said that here. Okay. Now this is a really oversimplified model. We don't really understand what's everything that's in the bulk. There's extra stuff. But it's saving grace. The reason that well, some of us have devoted so much time to it is we have an explicit representation of the entire, quote, gravitational path integral, an integral over this auxiliary field and its partner called sigma. And so we've got the entire path integral in this toy. And so we can poke around and see what strange things there are in it. And that's nice to have control like that. Now, suppose we compute two copies, an L and an R system. Then we have to consider auxiliary fields, left fields, right fields, but also fields that connect left and right. You can have a collective field with a psi left and a psi right. Well, in a geometry that turns out to contribute is this wormhole geometry, the space-time wormhole geometry. And in fact, you find a saddle point field that's non-zero at low temperature. And this is the thing that describes the ramp in the SYK model. There's no paradox here, there's no factorization, because averaging over these couplings, the couplings are the same in the left and the right system. So averaging over these systems introduces explicit correlations between left and right. And so the result need not factorize. And this is an expression of that. All right, well, the new thing we'll be able to add is we're going to be able to write a collective field integral for, let's say, this product, Z left, Z right, for fixed couplings. Usually you'd integrate them out. The expressions are simpler, but you don't need to. And this connection between collective fields and studying these factorization issues, at least in Hilbert space factorization, was talked about by Daniel Harlow and in various ways by Harlow and Jaffress as well. Well, if you have fixed couplings, what happens to these wormhole configurations of the collective fields? If they remain, and they will, how does this thing manage to factorize, as it must? Because then you have the gauge gravity dual connection. Well, the goal is we think we know the entire gravitational path integral. So tautologically, it must work. How does it work? It turns out we can study this problem in some detail only in a toy model. This should really be a toy model of the toy model. SYK with just one time point. Then if it's just got one time point, you're not integrating over bilocals, you're just integrating over ordinary numbers. You get ordinary integrals, and those we can really poke around in. And that will be the exercise. So this is always a good strategy to reduce things to absolutely trivial examples and see how things work. I have to tell you though, as I look back, we should see how far we've fallen here. In some sense, our interests, many of the interests of many of you here, is to study nature, like quantum gravity that's realized in our world, quantum gravity of black holes at the center of the galaxy. For a quarter of a century, we've retreated to this wonderful walled garden of ADS-CFT where we have precise control of definitions, and it has black holes in it. These fine-grained questions, these are all kind of non-perturbative questions, are hard to address here. And so we've retreated to this SYK model, this ordinary quantum system. We now have to retreat even further to one time point. But here, I hope at least we can make a stand. And then the question is, how far back can we push? What we'll find, and I'll give you the bottom line in case I don't get there. I'm already a half an hour in. We'll find that wormholes persist with actions that depend only weakly on the choice of fixed couplings. But they're new half wormhole saddle points with actions that depend strongly on the choice of couplings. And together, this set of saddle points gives the correct answer, which factorizes. So these provide the noise, the dependence on ensemble. These are there, but they don't. We expect, although we have not proven, that the same story holds in full SYK. We can give a plausibility argument, but certainly not at the level of detail we can analyze it in this toy squared model. Well, here, let's start being concrete. This is SYK with one time point. All right. Instead of having 4 fermions, we're going to study Q fermions. And this product that was before psi A, psi B, psi C, psi D is this product of Q different fermions. But here we're considering fields at one time. We've replaced a Grassmann field, which is what you do to make a path integral of a fermion. We've replaced it by a Grassmann number. So the path integral that used to be over Grassmann fields to define the quantum mechanics is now over n Grassmann numbers. And you write something like the action E, the I is because I have careful colleagues. These are these JABCDs. And this is the product now of Q Grassmann numbers. Now the J tensor is drawn from a Gaussian distribution. These are its moments, just in case you're interested in. And we can write similarly a model for 2 copies. They're often called replicas in this game. Z left times Z right. It's an integral over 2 sets of n Grassmann numbers. Same coupling for left and right. And then so this is the thing we want to study its factorization properties of. Well, let's calculate the ensemble averages of 1 partition function and 2 to find wormhole saddle points. Well, it's easy to see just by expanding out the Grassmann, the exponential, and using the rules of Grassmann integration, that the average over J's of Z itself is 0. So 1 copy has no interest in collective fields since G left left, which is psi left times psi left, the square of a Grassmann is 0. So there's no disk contribution to the partition function here. That's okay, we don't care about the disk, we care about the wormhole. But the average of Z left right, Z left times Z right is non-zero. So let's see how you calculate that. Well, we're going to write this collective field integral representation for this and just to illustrate how it's done. This is the defining formula. Let's average over J. It's a Gaussian integral. So you complete the square and you get psi left times psi left, because Grassmann squared is 0, you don't get that. Psi right times psi right gives 0. So you get psi left times psi right. You rearrange the terms a little bit and you find it's psi left times psi right, sum on indices raised to the qth power. Now you want to manipulate that. First, we insert a factor of 1 into the Grassmann integral. That's the way you insert collective fields, auxiliary fields. You just put 1 into integrals. You don't do anything. Okay, but you hope when you do this, you'll get better approximation techniques. Okay, and then you say, well, like this is equal to that because of the delta function, so you can't stop me from putting this here. So this is 1, you stick that in there. Then you represent this delta function by a Lagrange multiplier. Sigma is integrated on the imaginary axis here. So that's the thing that implements this delta function. Well, so now you interchange the order of integration. That's what you always do. You integrate out the Grassmann numbers. Well, let's see, what's the right thing to say? You can integrate out the Grassmann numbers, and what happens is that this term cancels this, and you're just left with, this term, this Grassmann term cancels this. So you don't have any psi side of the q, which is hard. You're left with g to the q and sigma times the fermions and sigma g. You integrate out the Grassmanns. The Grassmanns now only appear bilinearly times sigma. So it's a quadratic integral. You can integrate it out. Well, this is what you usually get a Pfaffian, but here you just have a single Grassmann number for every I. So integrating out gives a number, sigma. You have n of these, so you get sigma to the n. So you get an integral. It turns out to make the integral convergent, you should rotate these contours. I'm going to leave off the left-right indices just to make the formulas less simple. And you find this explicit integral. It's a two-dimensional integral over complex variables evaluated on two contours of this particular form. This was, again, this e to the n log is this Pfaffian term. The I sigma g is part of the delta function, and this is g to the q. Now, it's useful to break this up into this form where you keep the sigma g and the g to the q, and then you call this the result of the Grassmann integrals. This is this Pfaffian contribution. So this is the expectation value of this part that just has sigma that gives it the Pfaffian. But now you can vary this and find saddle points at large n. That's what you usually do with collective fields. Well, it turns out the saddle point equation, if the original variables look like this, they're very simple. These are differential equations. These are algebraic equations, pretty simple ones at that. So the solutions are g left right are the qth roots of unity, and sigma are essentially the same. We interpret these saddle points where g left right has got a sizable Web as wormholes. And it turns out when you look into the integrals, the correct prescription is you have to sum over all the saddles with equal weight. And so here I just said that the Web of g left right is a wormhole. It describes strong correlation between the two decoupled theories because you're summing over the couplings. And so we represent this thing being non-zero by this like line between these two time points. And the analogy is that's like this wormhole configuration. Here we don't have any time left. So it's like we're just picking a slice like that. Well, now it turns out it's interesting to compute the variance because we want to understand these fluctuations with coupling. Well, so now this is a more sophisticated thing. You have lots of different fermions, and so you need collective fields for left times right, left prime times right prime, LL prime, RR prime, LR prime, and RL prime. Okay, so you have like 6 of these collective fields. And so then you just do the same thing. You have more variables, and you look for saddle points. And you can find this set of saddle points where that line corresponds to picking this thing to have magnitude 1. I won't worry about the summing over these Q things here. It all works out. Well, you can have left right being 1, and L prime R prime being 1, and L prime being 0, L R prime being 0. So there's that configuration. There's that configuration. And there's that configuration. It turns out there are other saddle points that don't make a contribution. Either they're subleading at large N or they're off the integration contour. So then you can see that this moment is 3 times the 2-point function squared. So ZLR has a variance of order the signal squared again. You can see that these pictures are the dimensional reduction of these pictures. Well, now let's notice for future reference that in this pattern, sigma left right, which is related to G left right, has magnitude 1. Here and here, sigma left right is 0. Okay. Hold that thought. We can also write a G sigma integral for Z left and Z right for fixed J's. Now we're getting to the nub of it. Okay. This quantity should depend sensitively on which collection of fixed J's you choose because the variance is of order the signal squared. So we should find something when we do this that depends a lot on the J's. We just repeat the steps from the average case. We introduce a factor of 1 for the delta function, represent the delta function as an integral over sigma, integrate out the Grassmann numbers, and rotate the contours. Now, because we're not integrating over J's, we don't have this nice thing where the J couplings turn into psi side of the Q, which cancels this. This is the Grassmann dependence of the non-average theory. If you integrate over G's, then this cancels this, J's, this cancels this. But here it doesn't, it just appears there. And remember, these are products of Q fermions. So if you integrate over J's and compute this average, then you are back in the original expression. So now we can, as a toy model, we can write this thing as the integral d sigma dg of this factor. That's the same factor we had before. That's an explicit function, okay? You can do the g integral here. It's just some function. It looks kind of like an Airy function. If that were q were 3, it would look a lot like an Airy function. And call that function capital psi. And then we have this phi thing that is this result of this Grassmann integral that depends explicitly on the j's. That's complicated, but if n is 100, you can expand this thing out and you get this enormous polynomial in j's and sigmas from doing Grassmann integrals. This stops after a finite number of terms because they're Grassmann integrals. So this function is computable, although numerically it turns out to be quite difficult unless q is 2. But it depends on j's. All right, so all the non-trivial j dependence is encoded in this function phi of sigma. It's a black box for the microscopic information, if this were Super Yang-Mills or something, or a tensor model in SYK. We could compute it numerically, as I said, but even without knowing the answer for fixed j's, we can study its statistical properties for a typical j configuration and get some idea of where this integral is big and where it's small. Because the integral will make a big contribution where this thing is typically big. All right, so what happens to this boxed integral when we go from the average value of this to the non-average value? Well, something should change. The average value of this clearly just has the wormhole answer, but that doesn't have j dependence. So something has to change. So what happens when we go from the average value of this to the non-average value? We can do it by saddle point. Do the wormhole saddles at sigma equal 1 survive? Where do the other noisy contributions come from? This is now a one-dimensional integral. Okay, and we know that there's a big contribution from sigma equals 1, the wormhole saddle. Where on the sigma line does the rest of the stuff come from? That's the kind of stuff you can examine in great detail. But we find out where phi is big by computing its second moment. And if the ratio of the second moment to the first moment to the average squared is 1 or close to 1, then the contribution from that value of sigma is self-averaging. It's about the same as if you had done the averaging first. If this is much bigger than this, then it's non-self-averaging. And its contribution depends sensitively on the choice of j's. Well, we can compute this second moment. The second moment is a piece of this thing. And so we can compute it by introducing all these collective fields. Except here, we're freezing certain of the fields. So you compute it concretely by introducing a second auxiliary system. And we freeze sigma left right and sigma prime left right prime, sigma left right prime right, L prime R prime. Don't integrate over those variables. And it turns out, if you look in the forms, this is the same as phi squared at the geometric mean of these two. And we compute this by finding saddle points at large n for these other fields. And the location of these saddles will depend on these particular fields. So you do the saddle point calculation, you know, it's a little more saddle points. And then you compute the action. And you see, basically, if the action is the same as the trivial, if the saddle point that contributes to the average, the one we located, is dominant, then these things are the same, up to e to the minus n effects or fluctuation effects. And the thing is self-averaging. But if another saddle dominates here rather than here, these are very different, exponentially different. So you do this. Do the saddle points to get this and compare to that. I won't go through it. And this thing is got this explicit formula, sigma to the 2n. This is a picture in the complex sigma plane of where this ratio is big and small. Well, a good contour is to imagine that sigma goes out along a ray like this and hits one. This is a wormhole saddle. These are these for q equals 4. These are the 4 roots of unity. This picture is a q equals 4 picture. So let's ask along this ray what's going on. Inside the scalloped region, well, say outside the scalloped region, these two things are about the same. The system is self-averaging. The value of j's don't matter. The wormhole saddle lies outside this region. Its value doesn't change much if you change the j's. Inside the scallop region, that part of the integral over sigma, this depends a lot on which j's you have. So therefore, this thing has to make a pretty big contribution if the fluctuations are avoided the sigma. So we have to study like where in here is the biggest contribution from. Well, let's take the integrand, which is psi times phi, and let's take the root mean square size of this thing, not its average, but its root mean square. That gives us an idea of how big it is. And let's plot this. Because things depend exponentially on n, let's take the logarithm and divide by n to get a kind of action. And then this is a picture of that log integrand over n. Big things make big contributions. Small things make small contributions. This is the value 1. This is the wormhole saddle. This is the place that we've already located. This gives the signal. Then we go along here at sigma like a half or something, and you get an exponentially suppressed signal. But it comes back up to the equal size as it sort of must at sigma equals 0. This makes a comparable contribution to this, but it depends a lot on which value of J you have. This is its average value, its root mean square value. This thing we interpret as a half wormhole for reasons I'll tell you a little bit about. And so schematically, we have the non-average quantity is the wormhole saddles plus this half wormhole. It'll be a saddle point in a more subtle way at sigma equals 0. Now, suppose you'd look at the integrand where you take psi times the averaged value of phi. That's this red curve, continuing on this dotted line. It looks the same here. That's the self-averaging region. And then it goes off, in fact, to minus infinity, meaning that these things make an exponentially suppressed contribution. In fact, this thing is goes like sigma to the end, so the contribution of the integrand vanishes here. So that's why this dotted line goes off like this. And so in particular, this half wormhole contribution vanishes after averaging. For every fixed J, you get something big. For a typical fixed J, you get something big, but you average, they're positive and negative, and you get no net contribution. Well, let me try to give you a little bit of a more careful picture of what the integrand looks like. Here's the sigma line. This is the psi function. It's like an area function. It's sharply peaked, it turned out, around sigma equals 0. And this is a picture, we think of phi of sigma for a particular set of J's. You can compute its autocorrelation function, how much it changes from sigma to sigma. And it turns out its range of variation is much longer than the range of variation of psi. This goes like 1 over n to the 3/4. This goes like 1 over n to the 1/2. And so in the region where the integrand is big, this thing is locally constant. That's one draw, that's another draw. The mean is 0, but the standard deviation is quite big. And that's the contribution that we think gives the noise. Well, now let me try to motivate a little bit this word half wormhole. Well, again, so we're studying the average of the square, this quantity we're interested in. So here we imagine that we've doubled the physical system, L and R. So we did, as we did before, here's the LR system, and we just double it. This is some auxiliary, sometimes we call it a phantom system. We're just using to compute the second moment of this. We put in all these collective fields, and we find saddle points. Here's a wormhole in the physical system. Here's a wormhole in the phantom system. But now we have other contributions, and these are the half wormholes, where you have a wormhole connecting the physical left to the phantom left prime, and the physical R to the phantom R prime. This corresponds to setting the sigma variable not to the ordinary physical wormhole value, but to the value it would have in this phantom wormhole. And then you have another one here. Because this only involves one end of the wormhole, you don't have the field connecting this to this in the system you're looking at. We call it half of a wormhole. We don't mean it's geometrically half of a wormhole. We don't really understand it geometrically too long, but it involves half the fields an ordinary wormhole. And these are the saddle points that give the noise. So this just says what I said before. Well, it's interesting that in this factorizing quantity, the height of this curve was exactly the same. That sort of had to be because of the permutation symmetry of this picture. But these pictures obviously give the same contribution because they're just permutations of each other. But sometimes you can ask a question, what happens if you couple these two sides, these two partition functions? You can imagine putting an explicit fermion coupling between them in a quantum system, a wire between them. Maldacena and She studied something like that. Or you could have studied a correlated observable, something like the entanglement entropy between these two systems. That's something that you might do in a evaporating black hole story, where this is the black hole and this is the back. And then when you compute entanglement entropies, you're computing coupled observables. Then LR is different than LL prime. So there's no reason for these things to make equal contributions. It turns out, for the interesting values of couplings, this saddle point gives an exponentially larger contribution than this. Sorry, I'm in this slide. So then here's an example of the fermion coupling. So when you put this coupling in, it's not like the noise. It's not like these half wormhole contributions are absent. It's just they're exponentially suppressed. We expect that something similar happens in the replica wormhole version of this replica wormhole story, at least in the SYK version of it, which is discussed in this West Coast paper. In particular, there are replica wormhole saddles, but there are also replica wormhole, half replica wormhole saddles, but they're exponentially smaller in contribution. So the noise for the entanglement entropy is there, but it's just exponentially suppressed. This would also be true if you thought of making this coupling as mocking up a disk. So this noise is a ubiquitous thing of quantities. The thing about a factorizing quantity is essentially you have this permutation symmetry. And so the contributions have to be the same size. So factorization is a way of isolating the noise. You know, in some sense, the fact that replica wormholes have very low noise is a feature. It means you're pretty sure you've done the right calculation by just keeping the replica wormhole. But it's a bug if you're interested in the noise. And this is the kind of quantity that you can isolate the noise in. Well, I don't have a lot of time left, but let me briefly say what we think happens when you try to extrapolate the full SYK, which is a toy model in itself. Here's the lessons, I think, that this toy of a toy model produce. You find a region of collective field space that makes large contributions to the collective field representation of a quantity script Z. That could be Z left, Z right, or Z left, with fixed couplings. And you do it by studying the average second moment of this quantity. You add an auxiliary system, what's called not prime, but 2, and a physical system 1. You compute Z1, Z2, and you have to have these fields that couple physical to auxiliary. You study the saddle points of the full average 1-2 system. And you interpret the saddles with non-zero 1-2 fields as half wormholes, whose remnant in the physical 1 system are the vevs of the 1-1 fields set to their values in the half wormhole saddle point configuration. The half wormhole saddles should make large contributions to the integral for Z1 with fixed couplings, because they make a big contribution to the second moment. And because they average out, they should bend sensitively on the J configuration. Now, there's a lot of subtleties in this picture. Extra saddle points not lying on steepest descent contours that in this one time point model we can argue don't happen. But in full SYK, we can only argue the picture is self-consistent. So I'll just try to illustrate a little of the picture here in my final few minutes. So let's take full SYK and let's imagine computing one partition function. This is this microcanonical partition function that Phil has talked about. You take a microcanonical version of Z. Sometimes I'll put an L on it for one system. I guess I didn't put it here. And it's a complex quantity. Up till now, we've been thinking about real quantities. So this partition function averaged is described by this disk. To look for new contributions when this thing is non-averaged, you double it, add a one system, and then average a second auxiliary system, I'll call 2. And then compute the average of 1 and 2. Well, you have saddle points that are the disk in the physical system and a disk in the auxiliary system, plus a wormhole connecting physical to auxiliary. But this stuff is phantom, so let's just dot it. And what this means is that here, the G left fields assume their value corresponding to the disk geometry. Here, they assume a different set of values, because the geometry you're taking the correlator of is different shape. So this is one configuration of this bilocal in time, and this is another configuration. And the claim is that the contribution to this non-average thing is this value of G left, the action there, plus the action of this value of G left. You don't have a G1, G2, because this is phantom. It's half of this wormhole. So I think maybe I have a lot more to say, but I think maybe I'm going to stop after this slide and for questions. And then we can go on from there. So the picture we end up with is that Y for one copy is this nice Euclidean black hole, plus this half wormhole that remains, the thing you can diagnose by collective fields here. And I've just put this red circle here to mean it's noisy. And then the claim is, if you look at this as a function of time, this is the slope part that comes from the analytically continued black hole geometry. It goes away at late time, and you're left with this fluctuating thing as a function of time. The claim is that comes from this saddle point. And if you average it, you'll find 0. It just goes away. But then you could square it and get the wormhole. So you'd end up with a picture like, well, no, it'll take a little while to explain. Okay, so I'm going to stop there and entertain questions, and then we can go on. We can go on with material if we have time. So I'll let me take a pause for questions. Thank you.
All right, thank you, Steve, for preliminary stoppage. So questions?
That's a bad sign. Yeah.
Yes,
go ahead.
Oh wait, should I have raised my? Sorry.
Go ahead. Go ahead.
Why are you said that the half wormholes are suppressed when you couple them? I didn't precisely see that. Intuitively makes sense, but I didn't is there a precise argument for that?
You actually have to go and compute the action of them, and it depends on the sign you choose of the coupling, for instance. So it's pretty clear to say that the 3 saddle points will have different contributions, because with no coupling, all these time points are symmetric, and so these saddles can be mapped into each other by permutation symmetry. So they must have the same action. If you couple L and right, you break that symmetry. So these saddles will have different actions. But then it's a question of calculation about which one is bigger and which one is smaller.
Okay, I see. Thank you.
Okay. Mm-hmm.
Yeah, I did the first one dominates. Okay.
Because of the minus signs, when you do the calculation, this one dominates.
Yeah.
Over these two.
Thank you.
Mm-hmm.
I have a question.
Yes, please.
Could you go back to the slide with the sort of the capped off geometry, like the
disc?
Well, I guess it was the last slide you were on, the very last one.
Oh, you mean that red line?
Yeah. This one.
This one.
Yeah. So could you sort of think of that, like could you put some sort of effective theory on that sort of, I guess, that noisy line, and just sort of think of it as some sort of like quantum gravity system in the bulk that produces this noise?
We would love to do that. That circle is supposed to persuade you to think along those lines. We don't know in this SYK model of a candidate. I mean, people talk about end of the world brains as that live here, but we don't know. We've built a kind of effective model where you put a boundary condition here that's weighted by some random numbers that does that. But this is the big mystery, and the mystery you're asking about is what is the microscopic bulk realization of this noise? You might think these might be related to things that are called fuzzballs, geometric realizations of microstates. We just don't know. What we do know is that there's a region that's dominated by a saddle point for these parts of the fields. We don't know what's going on here. But that you've just put your finger on the big question in the subject. In some sense, we've encapsulated what's happening here by this black box I called phi of sigma. And the big mystery is to pull the top off the black box, open up the black box. And that is the question about how the bulk realizes the microscopic information that the super Yang Mills produces. That is the biggest, subtlest question in the subject.
Okay, thank you.
Yeah, well, if you have an answer, well, I was going to say tell me about it. Write a paper first, then tell me about it. Okay.
I have a question.
Yeah, please.
So in these tensor models of Klebanov and Tonopolsky,
Yes.
there you have one choice of the couplings, but the model looks like the averaged SYK model. So what would you expect the half wormhole story to be in those tensor models?
I would think when you say it looks like the averaged, that's a really good question. When you say it looks like the averaged SYK model for certain quantities, okay? Like for instance, computing a correlate or a partition function. So I think it would have a picture very much like this. The question you're asking is, you think of the tensor model as one draw of the random couplings. So that would be like the value with one set of J's, except it wouldn't be kind of drawn from a random distribution. It will be drawn from this rather structured set, where you'd have ones and zeros corresponding to the symmetry stuff. The fact that it gives an answer that looks a lot like this suggests that it's a typical set of J's. And if it's a typical set of J's, then it should give a contribution like this. You could write a G sigma integral for the tensor model, if you could integrate out the fermions numerically. Okay, and then our claim would be it would have a saddle point, and its value would be some particular number that would indicate, I mean, the particular value the tensor model assumed at this time or this time or this time. But there would be a bulk realization by something like this. You can see in some sense, you don't have a choice. If you can write a G sigma integral for any system, and that's just this manipulation of putting in 1 in the functional integral, we know that these quantities are noisy. So the noise has to be contained in the G sigma integral. The question is where? Like, does it completely screw up all the saddle points? You're just doing some crazy integral over this big space and you get plus and minus signs and cancellations. It seems that the large contributions are localized at large N. And you have this kind of geometric Euclidean black hole plus another place. And it's knowing what's going on at that other place that's the mystery. And we know kind of what G left looks like here. And that tells us kind of like what correlators would be on this geometry. But we don't know what's going on here. I can tell you what the G left configuration is. That's in some sense all that we know. But what we need to do is we need a better model where we can dig into the bulk more thoroughly.
Other questions? Let me ask you, Steve, a follow-up to the previous.
Yeah.
You had a correlator. It looks from your pictures like you might expect that as you take the 2 points close together, the two contributions would be the correlator.
They will be the same. Yeah. The short distance behavior of G TT prime will be the same. But when you go out kind of order thermal distance, they start deviating.
Okay.
And the weighting factor will depend sensitively on the coupling.
And if you think of multiple boundaries where you already in your system itself, before you sort of double it, you have multiple boundaries, you would have.
Yeah, you'll get something like this. Suppose you have L and R.
Good.
Okay. Then you double this and you get this wormhole and a phantom wormhole. But you'd also have something like this. So in the non-average situation, you'll get the ordinary wormhole plus a pair of half wormholes. And this line means something that I won't get into now. But this would be the picture for what we think. This is the thing that restores factorization when you don't average over coupling.
And you could also have in the top line, you could also have a contribution that has just a single connected.
Oh yes, sorry. Yes, you'd have disks here, but at a long time the disks go away. So I'm just imagining throwing away the disks.
Okay, and also, but on the subleading thing, you would also have a single connected 4-boundary wormhole, and the statement is that is completely.
Oh yeah. Sorry, that we would imagine that's suppressed by topological reasons. Good. That's got exponentially small Euler character. I mean, e to the minus whatever it is, you know what I'm saying, e to the minus 2s down or something. Okay. Because it's a more complicated topology.
Good.
Sorry, I didn't understand your question.
Yeah, just a question. Does the pair of half wormholes precisely cancel the wormhole contribution so that you only get the disks and that's how you get factorization? Or does it just make the wormhole contribution factorize, but it does give a non-zero contribution?
It's the second possibility.
Okay, thank you.
Because after all, we know that, I'll actually, since you asked, I'll show the next slide. We know that this is what one copy of the system looks like. It's that plus that. At late time, this goes away, so forget it. So that's what one copy looks like, is this noise. Factorization means that you get the modulus squared of this. So it's not zero, it's just this noisy thing squared. It's that ramp in the picture. So the claim is that this thing must add up to the ramp, this thing makes the ramp, plus this is the noise on top of the ramp. So what factorization says is you need an equation that says this thing is equal to this thing. And you say, gee, how can this be? You have 2 half wormholes here and 2 here. It turns out when you evaluate things with a G left right field present, the action for this configuration is different than the case where you have no G left right field at all. So here you can imagine you're doing a G left right integral. Here G left right is not 0. Here G left right is 0. But you could also evaluate this integral by not looking for G left right saddle points. You could just integrate all G left rights out and you get 1 because it's an auxiliary field. Then you just have left, left, and right, right. You get these configurations with a different action. And so at the end of the day, factorization is expressed in this kind of equation. You have a G left right field, and you have G left right is not equal to 0. G left right equals 0. These are two different saddle points in the G left right semi-classical evaluation. Or you just integrate the whole field out on a contour. You have no G left right. Then all you have are these half wormhole saddle points for G left left, and it has a different action. The entire integral of G left right is different than pinning it at 0. And so that's the way this equation is satisfied.
Okay, that makes sense. Thank you.
Okay, it's actually, well, it's kind of confusing. It's still confusing to me, but this is the way it works.
That's something.
Yeah.
In the tensionless string model of Eberhard and collaborators, they obtain
Yes.
factorization. Is that by
Yes.
this mechanism, or is that something different?
That's a really good question. I think in the model that Eberhard studies in his more recent paper, he claims not to know if they have a wormhole contribution or not.
Yeah.
The model is not chaotic, so you might not expect a ramp. There is a profound similarity that was pointed out by Bauer Muhammadjanov, who's a postdoc at IAS, between the two models. This one and that I find really interesting, and it turns out these models, as you know, are so simple. You know, you can just imagine where's some Grassmann expression. Here's some. Let's imagine you don't do all this collective field crap. There's a Grassmann expression for phi of sigma. You can just expand this out in powers of sigma. Do these Grassmann integrals, and you get these contributions from J's. And then you could say that would form some perturbation series in large N. It turns out. So you could take the wormhole saddle, the half wormhole saddle at sigma equals 0, and just evaluate all the fluctuations around it. But that sum truncates because you only have n Grassmanns or 2n Grassmanns. It's just some big polynomial in sigma. And so the series, it's a series that turns out in 1 over n to the q minus 2, I guess. It stops at a certain order of, you know, after the nth power. But it turns out that if you look at the terms, and it's not hard to see, that you find terms that start decreasing, as perturbation theories always do, and then they start going back up again. That's a feature of asymptotic series, actually. And the last term turns out to be exactly the same, or well, up to fluctuations, as the full wormhole saddle. So just doing the perturbative expansion around the half wormhole saddle, which is manifestly factorized, gives the full wormhole saddle. And vice versa, you can take the full wormhole saddle, do perturbation, and you get the half wormhole saddle. So it's not like you need both of these configurations. It's also okay to take one and then perturb around it. And we had sort of seen this, but we didn't know what to make of it. But what Muhammadjanov did is made the beautiful connection that this is the kind of thing that Eberhard sees. He takes the thermal ADS and expands and wrapped strings, these world sheets that wrap around the thermal circle, and finds if you do that sum exactly, you get the same contribution as the thermal black hole. Or you could take the thermal black hole and expand around it, or you could take one of the modular transforms. So there's this democracy of, you know, you can take a different background. As long as you do all the expansion around it, you get the answer. There's a question about why you don't sum over all the different backgrounds. Here, you're just doing an integral over sigma. You know, you're just doing this one-dimensional integral. These are just different ways of evaluating the integral. Suppose you said, I'm going to do this integral not by saddle point, This is the sigma axis. I'm not going to keep that plus that. I'm going to start here and do the Taylor series out, and it's a truncating series, and I must get the entire answer. So it's just different ways of doing the same integral. Doing it by saddle point, or doing this and keeping this. And it turns out doing one is manifestly factorizing. This saddle is manifestly factorizing, and you can argue that the perturbation expansion must be manifestly factorizing. So it's a terrible way to study the ramp, the averaged ramp, but if you want to study factorization, it's a good thing. And so this idea that there is a multiplicity of bulk descriptions, Eberhard, I think I don't know if you call it stringy ER equals PPR. I don't really like those words too much, but some kind of duality and modular invariance. That seems to smell right. Here, it's much more lowbrow. It's whether or not you include a G left right field or not. That's the, there are many different ways of doing the same integral. But after all, it's just one integral. Different ways of doing the integral have to give the same answer if you've done it right. And that's how I think miracles like this happen. It's just doing integrals on different contours. And when you do integrals on different contours, certain things can be obvious or non-obvious. Usually we do things on steepest descent contours, that's this. But because integrating G left right just gives one, sometimes it's easier to do that. So this is this is the hint that this model is providing about the way in which these kind of factorizing things might happen.
A follow-up question. This is different from usual QFT, right? Where you're supposed to add up all the instanton contributions and perturbations around the instantons, rather than just doing the perturbation theory around one vacuum and then.
You have to be careful about that. Actually, there's this theory called resurgence, where
that's what I had in mind.
I think if you do the complete perturbation series and Borel transform and do that integral, you find the instantons in the perturbation series. Mm-hmm. So the unknown thing there is how you fix the integration contours in the Borel plane, and that's usually need extra information for. And here you have the integral, and the series are convergent, so there's no ambiguity. But I think it's actually a lot like quantum field theory, where at the bottom you have a functional integral, and you can figure out different ways of doing it. Sometimes it's good to do by saddle point. Sometimes you might just do brute force, the perturbation expansion to all orders. Now, one of the things that makes this nicer is the perturbation expansion truncates. That's also true in Eberhard's model, I should say. You stop the number of wrapped strings at n. You can't have any more than that. So it's a geometric series. Here it's an asymptotic series. I mean, it's a more complicated series that goes down and goes up. But this, I think that's in any way, I don't really understand what's going on here, but I think it's a very interesting clue. And I'd like to understand it better. This paper of Mohammed Janov does some very explicit formulas. It's, I haven't completely digested it because I've been preparing lectures, but I think it's an interesting thing to look at.
Any other questions?
Hi, Steve. I have a question.
Yeah.
Do you think there's a good bulk description of a single member of the ensemble of, say, JT gravity, or do you think we need a more UV description to fully capture all aspects of the theory?
That's I'm not sure I have a good answer to that. There's this long delayed paper that Phil and Shenyu Yao and I are writing about. If you, it's not like you take a single member of the JT ensemble, but you take almost a single member. You know, like you don't actually, what would it mean to take a single member of the JT ensemble? It would mean taking a single random matrix or maybe a single set of eigenvalues of the random matrix. Suppose you don't say it's absolutely fixed eigenvalues. Suppose you say you fix the density distribution, you know, as a coarse-grained way. Then you can build a kind of bulk description of that. If you actually fix the eigenvalues, then you find these things called eigenbrains in this interesting paper of Blomert, Mertens, and Verschaid. And a fixed eigenvalue is like one of these FZZT brains. And so you'd have a sort of a theory full of those. And I think the bulk description, if it exists, is like that. Unfortunately, that's kind of out of control. The genus expansion is out of control there. And so you don't really know what the rules would be. So I think having a bulk description is kind of having some controlled way of getting at it. And that I don't see there. But there might be, I don't think it's a UV issue so much as a, well, it might be a UV issue. I guess I don't know the answer to that. But as a moral lesson though, we need another example. We need some other examples with a richer bulk. Here we've hidden a lot in this black box of phi of sigma. It would be nice to have some more bulk degrees of freedom that whose motion, if you will, makes these random numbers. And well, there's some hints in this model of yet another part in the integration space that's more like that, but I don't understand that. We need better models. And these problems are insanely difficult, and so you know I guess I would like to have another toy that's at least just one baby step up from these. I don't know, when you learn to drive, you have like a little tiny toy car, and then maybe you have a wagon, and then maybe you have a go-kart. I don't know what we need to progress to before we get our driver's license.
Great, thank you.
Sure.
Is there actually some sense of probing a single state, but with some very simple operator that would make the thing look coarse-grained enough to mock up just some bulk that you don't see the microphysics, but can't.
You're asking in a theory without kind of fluctuating couplings? Is there some way of doing an average over states that mocks up the ensemble? Is that the kind of question you're asking?
I want to fix the couplings.
Yes. Okay.
I want to look with not arbitrarily refined,
yeah,
or just some coarse-grained picture. And
yeah, the kinds of observables that don't depend on the couplings and that are realized where you don't have to worry about this noise are what we call these self-averaging observables. So for instance, a correlation function at short times, your quasi-normal modes won't depend on the specific choice of couplings. The black hole picture will be just fine.
Okay.
But if you take the correlation function and go to long times, you'll find the fact that the correlation function will start oscillating erratically. Just like this, what did I do here? Just like the, you know, this spectral form factor is supposed to be a caricature of that. This would be, morally speaking, there must be a faster way to do this, but this would be like your quasi-normal mode decay. But then it doesn't go all the way to zero because there's some graininess in the system. And from the boundary, we know the graininess will make the 2-point function look something like this. And so this part will have a nice effective description. It's what we call self-averaging. After all, we took this one sample lies right on top of the average here.
Mhm.
But then it breaks away here, and it's what we call non-self-averaging. And this noise is the hard stuff.
But for any time, when you're already within the ramp or even plateau,
Yeah.
you'll not be able to find some operator that would just self-average. Well, in fact.
Well, it depends. I mean, if it's got long times in it, no. I mean, I'm not sure what it means at long times to be on the, what it means to take an operator on the ramp. A ramp is like the ramp is only when you have operators at quite different times.
Right, so correlator of many simple operators separated in time by arbitrarily long times.
Will be a problem.
Okay.
In general, that will be a problem. Now, these are exponentially small signals. I mean, for all practical purposes, who the hell cares? Most condensed matter physicists completely ignore such things. I mean, well, that's not true. They often study what are called mesoscopic systems, where you make n very small, and these effects become appreciable. Study things called quantum dots and things like that. But in typical, studying a metal or something, these kinds of effects are just completely ignorable. For us, because they seem to be related to these very subtle issues about getting information out of a black hole and so on. Well, I don't know. I think whether we're focused on them. I'm not sure that's a profitable thing or not, but that's where we are.
Okay, fair enough. Any last question before we stop the recording?
I guess I had a quick question, Professor.
Please.
I guess I asked Dr. Said about this a little bit, but has there been any work on like the flat space limit? I don't even know if that if that's an appropriate question.
Yeah,
that's in ADS, right?
Yeah, that's a good question. I mean, one of the ways in which it's important is that, like, these times are very long. Let's say the evaporation time of a flat space short-shell black hole is of order the entropy, or twice the entropy or something, measured in thermal, I guess measured in thermal units. Well, measured in some reasonable time. It's measured in the initial Hawking temperature. It's goes like the entropy. Now, it turns out, if you are careful with this part, you can see that this ramp extends down much earlier than this. It doesn't. You don't need exponential times. It actually starts setting in at logarithm of the entropy. It turns out it's not the scrambling time, but it's got the same dependence on entropy, different coefficient. So even for a flat space black hole, you'll see just the beginning of this. But you won't be able to probe at very long times, very small energy differences to see like the plateau or something. This would be an exponentially long time. So I think the beginning of this behavior you would be able to see in flat space. But now there's a question. Usually what you do to stabilize a black hole in flat space, you might keep feeding it. But when you couple it to an external system, I think you wash out some of this stuff. So that probably is not the right thing to do. Yeah, you probably want to study it for this window between log S and S. And then you'd see a hint of these same phenomena. It's a very small signal. Maybe there'll be a problem in actually collecting enough photons to see it over that time. I'm not sure. I haven't thought too carefully about that. The question that people usually talk about are these kind of questions about studying scattering, like the black hole S matrix. If you prepare a fixed, very complicated state of quanta and scatter it off the black hole, that will have noise in it. So rather than studying long time, you study complicated matrix elements. So instead of studying the long time correlator of simple operators, you study the short time correlator, like an S matrix and 10-second scattering, of complicated operators, states with order S photons in them, or S gravitons. So that correlator, that matrix element of complicated operators will depend a lot on which operator you choose. So we'll have similar characteristics. We haven't done it, but I suspect Douglas Stanford has shown how to compute those matrix elements in the average case using wormholes. And so I think it's very likely that in the non-average case, there will be half wormholes there. And so that's what you would have to do in flat space to really get I think a fully developed type of signal like this.
Thank you so much. Cool.
Sure.
Anything else? All right. Well, let's thank Steve again.